Welcome back for another deep dive. Remember our series on MySQL Replication Basics?
Yeah.
Well, today we're diving into a real pain point for DBAs, replica lag.
Ooh, yeah.
You've got this awesome database humming along, but the replica's lagging behind, serving up stale data. Not good.
Not good at all.
We've got some great insights from Kedar Vajnaperker to unpack today to really help us understand, well, first of all, why this happens,
Right.
and more importantly, what you can do about it.
Yeah, so at its core, replica lag is just the delay between when a change happens on your main database server and when that replica catches up.
Okay, so break that down for me. What does that actually look like in practice? I mean, what are we talking about here?
So imagine a write operation happens on your primary database at, say, 8.05.000 a.m.
Okay.
But for some reason, your replica server doesn't get that update and apply the change until 8.0505 a.m., that 5-second gap.
Yeah.
That's replica lag. And while it might seem small,
Yeah.
those seconds can add up and cause real problems.
I think a lot of people outside of database administration might hear 5 seconds and think, what's the big deal?
Right, right.
But I'm getting the sense that even small delays
Yeah.
can have kind of a ripple effect.
Absolutely. Think about it from a user's perspective.
Yeah.
They might see outdated information,
Right.
which erodes trust and can lead to bad decisions.
Uh-huh.
Or imagine needing to fail over to that replica because your primary server crashes.
Oh, yeah.
Suddenly you risk losing those 5 seconds worth of transactions, potentially even more.
Yeah. Yeah. Okay, so we're talking about data consistency, user experience,
Yeah.
and even disaster recovery.
That's right.
This lag issue is a bigger deal than it might seem at first glance.
Yeah.
But before we jump into solutions, let's try to figure out why this lag happens in the first place. Kedar outlines 4 main categories that can cause this.
Yeah.
That's like a detective story.
Right.
We've got network issues, problems on the main server, things going wrong on the replica side,
Yep.
and even quirks with the data itself.
Right. So let's start with the network.
Okay.
Often network latency is kind of the prime suspect. Think of it like rush hour traffic.
Okay.
Congested networks
Right.
or long distances between your database servers,
Yeah.
that can just cause delays.
And I imagine dropped packets don't help either.
Yeah.
It's like almost like losing a letter in the mail.
Right.
It's going to cause a delay while things get resent and all that.
Yeah.
So we've got congestion and packet loss on the network front.
Uh-huh.
What about the servers themselves?
Well, sometimes the main server, the primary database, can become overloaded
Okay.
and struggle to keep up. Imagine trying to cram more clothes into an already overstuffed suitcase.
Yeah, I've been there.
That's your server when it's hit with tons of write operations,
Right.
long transactions, or huge data dumps.
So the server's just slammed with work and it just can't keep up. That makes sense. And I bet resource constraints play a role here too, right?
Right.
Of course, yeah.
Like not having enough processing power or memory.
Exactly. If the primary server is starved for resources,
Yeah.
everything slows down, including replication.
Makes sense.
Yeah.
But even if your network and your main server are running smoothly,
Right.
you can still run into problems on the replica side.
Uh-huh.
What kinds of problems are we talking about here? Is it just a mirror image of the main server issues?
Not necessarily. One of the biggest bottlenecks is that, by default, MySQL Replication uses a single thread to apply changes from the main server.
Oh, wow.
It's like having one overworked employee trying to process a mountain of paperwork.
So you're saying that even if my network and master server are top-notch, the replica itself could bottleneck the entire process.
Yeah.
Because it's stuck doing one thing at a time.
Yeah.
That seems like a pretty big design limitation.
It can be, yeah.
Yeah.
And just like with the primary server,
Yeah.
resource limitations on the replica can also lead to lag. If it's not adequately provisioned with CPU, memory, and disk I/O, it'll fall behind.
Okay, so we've covered network woes and server struggles.
Uh-huh.
What about that last culprit Kedar mentioned? The data itself.
Right.
How can the data itself cause replication lag?
Well, certain characteristics of the data can create friction in the replication process.
Okay.
Large transactions, for instance, are like trying to move a grand piano through a narrow doorway. It takes time and can hold up everything else behind it.
So the size and complexity of the data being moved can impact how quickly the replica can process it.
That's right.
What other data quirks should we watch out for?
Schema changes can also cause delays. Imagine adding a new column to a massive table.
Right.
That's a significant change that needs to be replicated, and it can take a while.
Yeah.
And then there are data inconsistencies,
Of
which can really throw a wrench in things.
Data inconsistencies.
Yeah.
Give me an example. What does that look like?
One common scenario is missing indexes. Think of it like trying to find a specific book in a library with no card catalog.
Okay. Yeah.
The replica might have to scan the entire table,
Yeah.
which takes much longer than a targeted search.
Okay. That's a great analogy.
Yeah.
So we've got these big, bulky transactions,
Yeah.
schema changes that disrupt the flow,
Right.
and data inconsistencies that make the replica hunt for information.
Yep.
It's like a recipe for lag.
Exactly.
And the thing is,
Yeah.
you might not even realize you have a lag problem until it's too late.
Right.
That's why monitoring is so crucial.
Mm-hmm.
So let's talk about that. How do we even know if we have a lag problem brewing?
Mm-hmm.
What tools can we use to keep an eye on things?
There are a few different approaches. The simplest is using the show replica status command.
Okay.
It gives you a quick snapshot of how far behind the replica is,
Right.
measured in seconds. It's a good basic check.
Okay, so show replica status gives us kind of a quick temperature check.
Yeah.
What if we want a more detailed view?
For more granular insights,
Uh-huh.
there's a tool called Percona Toolkit's PT Heartbeat.
PT Heartbeat, what's that all about?
It's a script that provides very precise measurements of replication lag.
Okay.
It's more accurate than just using show replica status and can give you a better understanding of what's happening.
So PT Heartbeat gives us more precision.
Mm-hmm.
Are there any tools that provide like a visual representation of this lag?
Absolutely.
I'm a visual learner, so graphs and charts always help me see patterns more clearly.
For real-time visual monitoring, you'll want to look at tools like Percona Monitoring and Management.
What?
PMM.
I love a good visual.
Yeah.
Graphs make it so much easier to spot trends
Uh-huh.
and see those spikes in lag that might indicate a problem.
Exactly. With PMM, you can not only see the lag in real time,
Yeah.
but also correlate it with other events,
Right.
like spikes in traffic or changes in server resources.
Mhm.
This can help you proactively identify and address potential issues before they become major problems.
That's awesome.
Yeah.
Okay, so we've got our monitoring toolkit ready to go.
Mhm.
We can get a quick snapshot with show replica status,
Right.
dive deeper with PT Heartbeat,
Yeah,
and get that visual overview with PMM.
that's right.
That covers the detection part.
Uh-huh.
But now, let's shift gears and talk about what we can actually do about this lag. Kedar breaks down solutions into 3 levels:
Okay.
architectural, configuration,
Mm-hmm.
and operational.
Right.
What can we do at the architectural level to address this lag?
Architectural solutions are all about laying a solid foundation for efficient replication. It's like building a house, you
Yeah.
want a strong structure to avoid problems down the line.
So if we're thinking about building this robust replication architecture,
Mm-hmm.
what are our building blocks? Where do we even start?
One of the most effective ways to combat lag is by implementing multi-threaded replication. Remember how we talked about that single-threaded bottleneck
Right.
on the replica side? Well, multi-threading is like adding more checkout lanes
Okay.
at a busy supermarket.
I like that analogy.
Instead of one thread handling everything, multiple threads can process different tasks concurrently,
Uh-huh.
speeding things up significantly.
That makes perfect sense.
Yeah.
Going from a single-lane road to a multi-lane highway, things are going to flow much more smoothly.
Exactly.
What else can we do at the architectural level?
Matching hardware between the primary server and the replica can also make a big difference. You wouldn't want to run a marathon on a scooter, right?
Right.
The replica needs enough horsepower
Yeah.
to keep pace with the primary server.
Right. So we need to make sure the replica isn't lagging behind simply because it doesn't have the resources to keep up.
Yep.
It's all about providing that solid foundation.
Uh-huh.
Are there any other architectural considerations?
If you have multiple replicas,
Okay.
you can use load balancing to distribute the read traffic among them.
Uh,
This prevents any single replica from getting overwhelmed and lagging behind. It's like having multiple servers sharing the burden, so no one gets overloaded.
that's a smart strategy. Spreading the workload, keeping things running smoothly, and preventing bottlenecks.
Right.
So we've talked about multi-threading,
Uh-huh.
matching hardware,
Yeah.
and load balancing as architectural solutions.
Right.
That's a great foundation.
Yeah.
What about the configuration level?
Okay.
What kind of tweaks can we make under the hood to optimize replication performance?
So configuration tuning is all about fine-tuning the engine, to
Right.
get the best possible performance.
Yeah.
One area we can look at is adjusting ACID compliance settings.
ACID compliance. Remind me what that refers to again.
ACID stands for atomicity, consistency, isolation, and durability.
Okay.
These are the properties that guarantee the reliability of database transactions.
Right.
And we can sometimes tweak the settings related to these properties to gain performance improvements.
Okay, so we're talking about potentially relaxing some of those strict ACD rules to gain a bit of speed.
Right.
Can you give me an example of a specific setting we might adjust?
Sure. One example is the inode flush logatrix commit setting.
Okay.
It controls how often the transaction log buffer is flushed to disk. By default, it's set to 1, which means the log buffer is flushed after every transaction.
Okay.
This ensures maximum data durability, but can introduce some overhead.
So if we're concerned about lag, we might want to change that setting.
Exactly. Setting it to 2, for instance, means the log buffer is flushed to disk every second instead of after each transaction. This can improve performance, but slightly increases the risk of data loss in case of a crash.
So it's a trade-off between durability and performance.
Right.
We need to weigh the risks and benefits based on our specific needs.
That's right.
What other configuration tweaks can we explore?
Another important setting is sync bin log. It controls how often the binary log, which contains the information needed for replication, is synchronized to disk.
The binary log, that's the heart of replication.
Precisely. By default, sync bin log is set to 1, which means the binary log is synchronized to disk after every transaction. This ensures high durability, but can impact performance.
So similar to inode flush logatrix commit, we could adjust this setting to improve performance.
Exactly. Setting sync bin log to 0 means the binary log is synchronized to disk at the operating system's discretion, which can offer better performance, but also introduces a slightly higher risk of data loss in case of a server crash.
Okay, so we've got these two settings, inode flush logatrix commit and sync bin log, that we can adjust to fine-tune that balance between durability and performance. What else can we do at the configuration level?
Tuning the binary log format can also make a significant difference.
Okay.
MySQL supports 2 main binary log formats, statement-based replication, SBR, and row-based replication, RBR.
SBR and RBR. What's the difference between these two formats, and how do they impact replication performance?
SBR logs the SQL statements that are executed on the primary server. It's generally more compact, but can sometimes lead to inconsistencies on the replica, especially with complex statements or non-deterministic functions.
Okay, so SBR is compact, but can be a bit unpredictable. What about RBR?
RBR logs the actual row changes that occur on the primary server. It's more verbose, but ensures greater consistency between the primary and replica.
So if we prioritize consistency over compactness, we might opt for RBR.
Exactly. Choosing the right binary log format depends on your workload and your tolerance for potential inconsistencies.
It's all about finding the right tool for the job.
That's right.
Any other configuration tricks we should have up our sleeves?
Yes. Remember that single-threaded bottleneck we discussed earlier? We can tackle that head-on with parallel replication by enabling this feature and adjusting the slave parallel worker setting. We can have multiple worker threads processing replication events concurrently.
So we can bring in reinforcements to help that lone worker.
Exactly.
It's like assembling a team to tackle that replication workload more efficiently.
Precisely. Parallel replication can significantly reduce lag, especially for workloads with many independent transactions.
Okay, so we've explored a range of configuration tweaks. From adjusting AC compliance settings to choosing the right binary log format, and even enabling parallel replication. That's a lot to consider. What about operational solutions? What can we do from like a day-to-day management perspective to keep lag under control?
Operational solutions are all about fine-tuning your systems and processes, to minimize lag. It's like keeping your car well-maintained, right? Regular checkups and preventive measures can help you avoid major issues down the line.
So what kind of maintenance are we talking about in the context of replication? Where do we even start?
One key area is query optimization. Remember how we talked about those complex queries or full table scans slowing down the replica? By carefully analyzing and tuning these queries, we can reduce the load on the replica and help it keep up with the primary server.
So it's not just about the volume of data being replicated.
Right.
But also how efficiently the replica processes that data.
That's right.
Makes sense. Any tips for optimizing those queries?
Make sure you have the right indexes in place. Indexes are like the table of contents in a book.
Right.
They help the database quickly find the information it needs without scanning the entire table.
So it's like making sure the replica has a good map
Yeah.
to navigate that data efficiently.
Right.
What else can we do from an operational standpoint?
Another important strategy is to minimize unnecessary schema changes on the replica.
Okay.
Every time you alter the structure of a table, it can create a temporary pause in replication.
Okay.
If possible, try to bundle those schema changes or perform them during off-peak hours to minimize disruption.
That's a great practical tip. It's like scheduling road work during the night.
Yeah, exactly.
When there's less traffic.
Yeah.
Anything else we could do operationally?
Yes. Consider using delayed replication for certain replicas.
Now that sounds counterintuitive.
Uh-huh.
We spent this whole time talking about how bad lag is.
Right.
And now you're suggesting we intentionally introduce a delay.
Right.
Why would we want to do that?
It's a strategic trade-off. Delayed replication can act as a safety net in certain disaster recovery scenarios.
Okay.
Imagine you accidentally run a massive delete operation on your primary server.
Oh, no.
Wiping out critical data. If you have a replica with a delayed setup, say 30 minutes behind, you have a window of opportunity to stop replication and recover that lost data from the delayed replica.
I see. It's like having a backup copy that's intentionally a bit out of date.
Right.
That way, if something goes terribly wrong on the primary server, we've got a chance to kind of rewind the clock a little bit.
Exactly. It's a trade-off between real-time consistency and having a backup plan in case of catastrophic errors.
Okay, so we've explored a range of solutions here, from tweaking hardware and configurations to optimizing queries and even strategically delaying replication. Is there like a one-size-fits-all solution to this lag problem?
Unfortunately, there isn't. The best approach really depends on your specific workload, your tolerance for data inconsistency, and the potential impact of stale data. It's like choosing the right car, you know? A sports car might be great for speed, but a truck is better for hauling heavy loads.
So if I'm dealing with high-volume, real-time transactions where every second counts, I might prioritize multi-threaded replication, powerful hardware, and maybe even relax some of those ACD compliance settings.
Exactly. But if your application is less sensitive to those real-time updates, you might opt for a simpler setup. It's all about finding the right balance between performance, consistency, and complexity.
You know, as we've been dissecting this whole replication lag puzzle, it strikes me that even with all the best practices and optimizations, some level of lag might just be inevitable.
That's a great observation. Even in the most finely tuned systems, you'll likely see some minor discrepancies between the primary and the replica.
So how do we know what's acceptable lag? Is there like a magic number we should be aiming for?
There's no universal answer. It really depends on your specific application, your tolerance for data inconsistency, and the potential impact of stale data.
So for a financial application where every transaction needs to be reflected in real time, even a tiny lag could be problematic.
Absolutely. But for something like a social media feed, a few seconds of delay might be completely inconsequential.
It's all about context.
Yeah.
So how can our listeners figure out what's an acceptable level of lag for their own use cases?
It starts with understanding the business requirements and the impact of stale data. Ask yourself, what are the consequences of serving slightly outdated information? Will it affect critical decisions? Will it lead to financial losses?
Right. So once you have a clear picture of the potential impact, you can start defining your tolerance for lag.
Exactly. And don't forget to factor in things like failover scenarios. If your primary server goes down, how much data are you willing to lose? That will help you determine how closely your replica needs to be in sync.
It sounds like finding the right balance requires a good understanding of the business needs, the technical landscape, and a bit of risk assessment.
That's right.
And, of course, once we've established our tolerance, we need to monitor things closely to make sure we're staying within those bounds.
Precisely. Monitoring is key. Even if you've defined an acceptable level of lag, you need to keep a close eye on things to make sure it doesn't creep up unexpectedly. That's where tools like PT Heartbeat and PMM come in handy.
Uh-huh.
They can provide early warnings if the lag starts to exceed your defined threshold.
Well, I think we've given our listeners a lot to think about today.
Yeah.
We've gone from defining what replication lag is to understanding its causes,
Right.
exploring a wide range of solutions,
Yep.
and even discussing how to define those acceptable levels of lag. It's been a true deep dive.
I hope so. And remember, replication lag is a common challenge. But with careful planning, monitoring, and optimization, you can keep your replicas humming along smoothly.
And if you're looking for more insights on MySQL Replication, be sure to check out our earlier series on the basics.
Yep.
It really lays the groundwork for understanding all the nuances we've discussed today.
Absolutely. And don't hesitate to reach out to the vibrant MySQL community for support.
Yeah.
There's a wealth of knowledge and expertise out there ready to help you tackle any challenges you might encounter.
That's a great reminder. The MySQL community is truly amazing.
It is.
Well, it looks like we've reached the end of our deep dive into MySQL replication lag.
Yeah.
Thanks for joining us on this journey.
Until next time, happy replicating.